watching this. I'm Eric Opoka, and this is our small presentation for the knowledge graph-based matching of pesticide property precision pest and disease management. So these are the main keywords. We have pesticide recommendation, lead chemical properties, pest and disease management, explainable, artificial intelligence, precision agriculture, efficiency as time goes. Let's move on. So here we have the content of the presentation. We have introduction, related works, problem statement, research questions and objectives, research contribution, methodology, system architecture, and mathematical foundation of each patent model, data set description, results, limitations, conclusion of future work, references, and acknowledgement. Let's move on. We have the introduction. So the introduction, I'm going to break down the keywords of the project. The first one, we have the knowledge graph. The knowledge graph should work in a way that we shall have the what we call nodes, which are the different nodes we shall use for the system, because the system works in a way that the vision transformer will detect the pest, then we shall link with the knowledge graph, which has crops, pesticide, and chemical data to link them up to come up with the best precision what results for the farmer. So this one explains reasonable, okay. It explains reasoning for explainable recommendation. So next we have pesticide recommendation. These are the pesticides we recommend to a particular farmer from the knowledge graph. Since we shall connect all the four major entities, the CSV data which we created, it will come up with a pesticide recommendation, which is precise for this case. So we have leaf chemical properties. Leaf chemical properties analyze the leaf composition and stress indicator. So in this case, we need to first analyze the chemical properties of a particular plant so that we need recommended pesticide, because sometimes we can give a pesticide which is not good for the plant. Moving on, we have pesticide management. Pesticide management, it detects and clarifies the crop diseases from images. So this is mainly how the system will work. We use a knowledge graph plus pesticide recommendation to analyze the leaf chemical properties to come with a precise pest and disease management for the particular pesticide, so that a particular farmer gets the results he or she wants. So moving on, we have explainable AI. Explainable AI is more like how the system will be combined to be. You get what I'm saying? So it will be an explainable AI which uses reasoning to come up with the results. So next we have precision agriculture, which applies AI to efficient driven data farming. So moving on, we have related works. Related works here, we have the work which is crop DP KG which 2025, of which in this case it had a what? An architectural limitation of no modeling of pesticide properties. So in this case, we came up with our system which works on this problem here. For this one, we model pesticide properties based on reasoning, of which for them it could not. So we have visual KG for pest, which was in 2025 also. This one is it has no physiochemical reasoning. So in this case, our system has a physiochemical reasoning which gives a particular pesticide and leaf to be compatible enough. So we have AKG for agriculture, which had also a limitation of no biological or chemical constraints. So it's too generic, not crop or field specific. So for our case also, it's kind of a little bit wide, which works on this problem. It talks on specific fields and the rest also. So we have tomato leaf knowledge graph, which is a knowledge graph for tomato disease. This one here, it had a problem of no multiple crop. For our system, it will be somehow robust to bring in all types of crop, which in this case also is lack pesticide recommendation, of which our system also does what we call pesticide recommendation. So next we have the CNN leaf-based disease models, which I'll not go so deep into it because time is running. Next we have pesticide label mining. Let's go to the next slide. We have problem statements. So our problem statements here are four major ones. We have high crop yield losses. So in this case, most farmers get high crop yield losses because they don't know that the best pesticide to apply, particularly sometimes diseases might come, but when they say diagnosis, then it's so subjective to different people. You can call someone who says something else, someone says something else. So in this case, the farmer gets a wrong one. So in this case, our system-based reasoning plus the vision transform to come up with something better. Get what I'm saying? So next we have the diagnosis. Diagnosis depends on experts. So in this case, it's low subject now. It's inaccessible, like I've said. For example, sometimes you have to call an extension worker, for example, if you're in the village, which will take time, and such extension workers are diagnosed subjective, which in this case sometimes it can be a wrong one. So with this knowledge graph, with this system here, you'll have it straight into your phone, which you can use to do what you want to do. So pesticide misuse, in most cases, people don't know the right quantity to apply. In this case, our system also provides the right quantity to apply for a particular pesticide being applied to a pest. So lack of the digital explainable tools. So in this case, we have people who don't have digital explainable tools. So in this case, you install in your device then you access from anywhere. So in this case, we have the digital explainable tools now at your fingertips. So next, we have the computational program. We have 4 main ones also. Noise and unbalanced multimodal data set. So in this case, our system works with almost 4 to 5 main different models. So in this case, the first one, which is the vision transformer, which getting the images were so hard. So in one case, you can get an image which has some biased data set. So it means some other crops have too many images than the rest. So in this case, it harms the learning accuracy. So next we have the for the text also. For the text, we have to create our own, because in most cases, for all the data sets we have been finding, it lacked most of the things we want, or it had some of the things we don't want. So we had to come up with our own things. So next we have semantic disconnect. So in this case, the system in one way or the other still works on representing information syntactically, not semantically, which explains all the reasons why something has been got to be a particular place, or something has been given a particular place. So multimodal fusion difficulty also. Integrating all those things was somehow hard, of which it took us a lot of time to integrate everything. In this case, we have the large vision encoder, which is the vision transform plus text, which is somewhat hard. So next we have black box prediction. In this case, some in one or the other farmer can doubt the prediction the system is making, because it's not based on real proper reasoning. It's just representing things syntactically, like I've explained above. So moving on, we have recite question. Recite question, we have 3 main ones, of which what AI model can accurately classify multiple live pest diseases images. So this is one of the recite questions we came up with. So next is how can structured pesticide data and unstructured chemical and agricultural text be integrated for knowledge-based decision making? How can explainable reasoning be incorporated into pesticide recommendation, improve trust and usability? So in this case, our research objectives: develop vision transformer based for high accuracy disease classification. So in this case, we have to train our system on vision transformer model. So in this case, the vision transformer detects the disease with high accuracy. Next, we have to construct knowledge graph linking the 4 different nodes we shall use in the system, which is the crop diseases, pest, leaf traits, and pesticide, and the chemical properties also using the knowledge graph. Next, we have to integrate the knowledge graph plus the natural language processing. With the natural language processing, it detects what we call the text from the different data we shall feed it on, because the data comes from food and agriculture organization. We have to extract what we wanted. So in this natural language processing, it will detect what we need from the data. So we have to design a system that is scalable across multiple crops. We have maize, tomato, and others future to come. So AI research contributions and outputs. We have AI research contribution. These were the ones we had. AI disease detection, of which we developed vision transformer, which detects accurately crop leaf diseases and agricultural images. Then we have to initiate knowledge graph fabrication. Knowledge graph, like I have said before, it had 4 main nodes, which is disease, pest, leaf traits, pest, which you can see as time goes. We have the NLP, enhanced pesticide intelligence. So in this case, the NLP is highly intelligent in such a way that it detects and extracts the text we want from the different text documents which has the chemical leaf properties and the biological traits of the leaves. So next we have decision support deployment. We shall deploy the AI, which works on what we call high precision based on the reasoning we have given it from the different data we have trained it on, right from vision transformer right to the natural knowledge graph of agriculture. Moving on, we have the methodology and system architecture. So this is how it will work. We have 4 main layers: the perception layer, knowledge graph layer, brain layer, and the action layer. So in this case, in the perception layer, we have the camera, which will be able to camera or mobile upload. You upload your image, then the vision transform detects the disease. Then in this case, the NLP engine goes and extract what it wants from the pesticide document and pest document, so which will relate together with the vision transform from the disease, because the disease is what it will use to detect what it wants from the document. Then afterwards, it comes to the knowledge graph layer, which has the 4 main major nodes: the pest, disease, pesticide, and leaf traits, to come up with the recommendation engine, which is the explainable scoring, the brain layer, which we will see in the demo. Then we have the action layer, which is the output of disease plus best plus safety notes. Moving on, we have the vision, we have the going into the specific models we use and explain the mathematical models we use. So in this case, we had the first, which is the vision transformer. The vision transformer will use what we call splitting images into patches. So in this case, the whole image is split into what we call patches, of which the patches, we have to get the patch embedding, which is more like the mathematical model we used in this case. So the patch embedding, we get it in this way. We shall have that what? Formula, of which the x is a vector, which presents the total patches which has been divided from the image. Then we multiply it with the weighted constant, which is W. The weighted constant, which is W, then we add with the bias. The bias BE, which is the bias, just to improve on the flexibility. So the weighted index is simply a constant we shall use to multiply, then we add. Then moving on, after getting the patch embedding, it will use self-attention to extract the relationship between the images, then use classification aid to get what we call the real disease in this case. So in this case, the attention has three main entities in this case, which are in the formula. We have the Q, which is the query, which presents a particular patch we are focusing on. Then the K, which presents other patches in this case. Then the V, which presents what? The value, which presents the information in the particular patch we are dealing with. Then we have the DK here, which is more of like, it is simply, we use it as a constant to reduce on big numbers, in this case, like you have seen there, to give us that formula. Then the softmax is more like a constant, which is used to return the result to a probability, which results to 1. So we have the classification head, which has that constant. We have the softmax, which the weighted constant, which you have seen in the above what? Patch embedding formula. Then we have that HCLS, which presents the token we are dealing with in this case, to give us the classification head. Moving on, we have the NLP model, which uses what we call the relation extraction, of which in this case, for the first formula, we use what we call text into embedding. So in this case, this X is what we call, is what we shall use as a constant to multiply with the transformer to give us, to convert into contextual embedding, this X, to convert the X into the contextual embedding, of which the X presents the input token, for example, a particular word, like for instance, a pest. So in this case, the pest is going what we shall use with the transformer to get what we call the contextual embedding from that particular input token of X, or like you have seen there. Then it initiates what we call entity relation detection, of which in this case, entity relation detection has those five major entities we shall use in this case of the EI. The EI is more like what? A particular, let me say, a particular word. For instance, pesticide, like pesticide is a particular word of itself. Then we have EJ, which is more like another one, which is what? A particular word again, which is pest. Then the softmax also, which is more like the what? The constant which is used to convert the result to a probability which equals to 1. Then the HI, which we had seen in the above formula here. The HI is what you're seeing here, the contextual embedding, which we had gotten in this case here. Then the softmax, like I had said before. Then the weighted index is more like constants, which we shall use to multiply all those things to give us an accurate result of the entity relation detection, like you have seen here. Moving on, we have the knowledge graph, which bases on reasoning layer. So in this case, the reasoning layer uses what we call graph scoring. Graph scoring has three main things it deals with. We have the S, R, O, and the F, of which the S is the what? Subject node. Subject node is like a particular word, like pesticide. For instance, pesticide, pest, then R, we have the what relation, which is target. For example, pesticide targets a pest, of which the pest is the object, node, like you have seen there. Then that function is what is the constant we shall use to multiply to give us the real score, like you have seen, that to get the graph scoring for that particular knowledge graph reasoning layer. Then moving on, we have the recommendation engine, of which this case is usually the weighted scoring criteria, of which the score here we have 5 major things to do. We have a target match, of which a particular disease must be able to be totally destroyed by a particular pest. That's what we call a target match, of which it has the T, capital T, of which you multiply with the weight 1, like you have seen there, but of which are more like constants which I'll get to choose. So in this case, we chose 5.0 as the way to multiply with the target match. Then the physiochemical stability. So physiochemical stability is more like the particular leaf has to be compatible with a particular pesticide, because in one way or the other, sometimes we might apply a particular pest which may destroy the particular leaf in this case. So they have to match in terms of their chemical chemical what components. The chemical components of the leaf must match the one of the pesticide so that it doesn't give any what dire kind of impact on the leaf. So next we have the residual safety. Residual safety is like the number of days the particular pest must last in a particular leaf. So you need sometimes if the particular pesticide it lasts for too long on the particular leaf, it affects the chemical making of the leaf. So in this case, sometimes you get people eating certain type of leaves which are not good for their use because of the pesticide we have applied. So sometimes if it takes too long, it affects in the future, even though when it comes to harvesting. Next, we have the ecotoxicity. Ecotoxicity is like the danger it poses on the environment. Get what I'm saying? We have given it E, the danger it poses to the environment, and we multiply it a particular way, 4, which is 0, which is 1.0. Then we have the recommended dosage. This is the dosage you have to apply to a particular, per spraying, let me say the amount of dosage per spraying. So in this case, it also gives what we call affordability, because sometimes if you spray too much and it's expensive, it affects the farmer in one way or the other. So in that case, the farmer will be able to know what he or she has to do. So moving on, we have the data sets. So we had 3 main data sets. The first one was what? Leaf images. Leaf images, we got it from Plant Village via Mandalay. It's a total of 4G because in this case, we are trained it on maize, which has 4 classes of, which has 21,000 images. Futures, it's in JPG format. Then it had that resolution, data space we are training to 70, 15% for training was 70%, validation was 3%, then testing was 15% also. Next, we had the pesticide. That's the description. We got it from Food and Agriculture Organization. We had to extract what we wanted because in this case, we could not take everything because it lacked a lot of things. We had to initiate what we needed. In this, of which some were from our end, synthetic in one way or the other because we could not find everything we needed from those data sets here. So the regional size was 10 MB. It had those tables, which I'll see in the tables as time goes, as we proceed. So it was in the form of CSV file. It consists of 200 active pests commonly used. So the method of operation, we use scrapping method here. So data set 3 was for pests, of which we got in the same way we got the other one of pesticide. It had those futures. It was in the format of CSV file, consists of 200 crop pests. So next we had the crop leaf traits. That's how it was. So that's the crop variety and the rest. So it was in the form of CSV file. The futures are those. It also consists of 200 leaf traits with their futures. So that's how the pesticide, that's how a sample or the data set for the pesticide was looking. So it consists of the name, cast number, molecular weight, log P with lipophilicity, water solubility, fever pressure accumulation, target test, toxicity level, residual days, application rate, then efficacy score, which were those. Then we had for the pest, which had those columns here. We have pest name, crop host, damage type, transmission symptom, fever condition, seasonality, economic impact. Moving on, we had also for the leaf traits, which is the crop variety, leaf length, leaf weight, chlorophyll index, nitrogen content, moisture level, like you have seen. So these are the results for the training. So for the first data set, which was the maize, like you have seen, we had those number of what? Those number, we divided everything to 70, 15%. For training was 70, 15% was for validation, then for testing, like you have seen. That's the class distribution. Moving on, we have class distribution in leaf trait. So the leaf trait, that's how it was distributed, like the number of what? The crop type plus the number of entries. That's the crop distribution in the leaf trait. So in this case, potato was somewhat biased because it had more leaf traits in this case. So we had pest or disease distribution by host. So in this case, grapes, it had 42. Apple had that. Then maize also had that. In this case, pest and disease distribution by host, the crop cost for the grapes was more in terms of the number of grape fruits. Hence, it was somewhat biased in one way or the other also. Then we had the what? Relationship type. These are the 5 method relationships we use, of which a particular pesticide is compatible with, a particular leaf is compatible with a particular pesticide. Then a particular pest affects a particular leaf. Then the particular pest is treated by a particular what? Pesticide. Then pesticide targets this pest. Then the pest is resistant to. So those are the relationship types we use in our knowledge graph, of which that's the count, again, the relationship type graph, which we came up with. So we had the EDA. Moving on, we had the correlation leaf biochemical traits, of which you have seen, which here it mainly relates the different what? Traits of the leaves with each other. Like for instance, we can choose one to say leaf length, of which in this case, for a particular leaf length, to connect a particular chlorophyll index. Like for instance, if a leaf is 1 centimeter, it has that chlorophyll index of 0.083, like you have seen, where they collide, which is here. That's mainly how it's explained. So that's the correlation of leaf chemical trait. Then the pesticide efficacy by toxicity level. So that's how a particular efficient pesticide is toxic on the environment. So in this case, the middle class, we have ones which are highly toxic, but also highly effective. You get what I'm saying? That's how it is. Then we had one which has moderate toxicity. Then there's one which has low toxicity level. So moving on, we have the cage illustration. So that's mainly how it will connect. So we have what we call a particular pest, which is Puccinia pilosora. It attacks the maize of that hybrid there. So in this case, this particular pesticide has this 5 main treatment, this particular pest, of which we shall use the weighted score to get the best for this particular hybrid of leaf. Moving on, we have model selection and deployment. In this case, the first one which we had to train was the vision transformer, which achieved 98% for maize. Then we have the distilled bud NLP from Hugging Face, the NLP model we use, which extract relation from the text. From text, then it gets into a knowledge graph. Then we have the knowledge graph, which we use network X and custom ontology, which predicts what we call the pest, which we use prediction to the pest, then to the pesticide. Then we have the hybrid recommender, which this is the recommendation engine we use, which gets all the above we had mentioned and come up with a particular knowledge graph rule engine. So the deployment and pipeline system, that's how it will work. We have the input leaf, of which the VIT model will detect the disease. Then the NLP will come up with the relation external knowledge graph query plus the explainable pesticide recommendation. So next we have the demonstration of the developed product, which I will do it the demo, but that's how it works mainly. We upload the crop leaf image via the mobile or web interface. Then the VIT model predicts the disease class with high accuracy, like for example, common rather than knowledge graph retrieve the link relationships. Then the NLP extract the formulation field, user notes from the recommendation engine, what generates the final pesticide. Then the limitations which we had with the data set constraint, like before, we had problems getting data sets because in one way or the other, for the particular like text, getting a data set was very hard because it missed a lot of what we needed. So we had to get some by ourselves. So the model generalization issue. So in this case, VIT was first trained with maize. So in this case, it's more accurate with maize. So therefore, in future, we shall get a way of extending it also, but that's still a limitation we have. Then semantic reasoning gaps. In this case, the method still works more like a black box, which works mainly on recommendation without proper reasoning. Then explainability limitations, of which in this case, it doesn't come up with its own explainability. We have to train it in one way or the other to come up with a particular recommendation. So the conclusion, future works here. Next, we will develop an AI-driven crop disease diagnosis and pesticide recommendation system, like I've said before. It has high accuracy of 98% for maize. And the knowledge graph also was highly interpretable, matching all the relations we needed in the system. So we had context explanation was highly achieved. Then the decision support for farmers was also highly achieved. Then limitation was still synthetic dependent. Some of the things in the we got it by ourselves. Then next we're going to expand the data set for more crops. You know what I'm saying? Then integrate real field sensors like sensor data, then mobile plus offline application, visual heat maps, document level, just scientific justification, field feedback, and so on. So the references are those. We have an image is 16 by 16 wide transformer for recommendation at scale, international conference learning staff. Then we have the part pre-training of deep biodirection transformer for language understanding. I will attach these slides on the video where you will be able to go through the references and everything so you understand what I'm talking about here. Then acknowledgement. We acknowledge Makerere University, the college where we come from, for the academic guidance, and our supervising lecturer for the continuous support, feedback, and domain insight. Then open source research communities like Hugging Face, PyTorch, Kaggle for helping us to come up with this work here and all the tools we use. Otherwise, thank you for listening.